Hi everyone, I'm Longyi.
I'm Renta.
We're graduate students from Columbia University majoring in electrical engineering. We designed a Class D amplifier chip for the VLSI Design Lab course, and today we're going to talk about it and give you a demonstration. Shown here is the block diagram for our Class D amplifier. The first block in the signal chain is the single-ended to pseudo-differential converter. It takes two input, left and right, sum them up, and converts to pseudo-differential. The supply voltage is 2.5 volts, and the reference voltage is 1.25 volts, providing the common mode voltages for all of the operational amplifiers. The overall system is a feedback amplifier with a gain set by the 100K and 200K resistors. The 10 picofarad capacitor sets the first pole of the amplifier, which stabilizes the loop. The 22 picofarad capacitors sets the dead time of the gate drive signals for the output device. This prevents any shoot-through in the output stage.
The basic principle of Class D amplifier is shown here. Input the audio signal into the comparator and compare it with the triangle wave signal to obtain the PWM signal, meaning that the input is encoded as the duty cycle of the pulse signal. The pulse signal and its offset then drive an edge bridge, turn on and off the power device to create an AC signal to the driver, and in between a filter circuit is required. The 500 kHz triangle wave is generated by an oscillator. The load capacitor is charged and discharged with constant current 10 microamp to generate the positive and negative ripples. The comparators and the latch generate the square wave to switch between charging and discharging for the load capacitor. But due to the hysteresis of the comparator, the actual frequency of the generator is a little bit smaller than the target. Since we have two different common mode voltage levels, 0.6 volt and 1.9 volt, we designed two comparators with NMOS input pairs and the PMOS input pairs. These comparators are also used in further pulse width modulation, and simulation results shows that the hysteresis of the comparators are about 30 mV.
The OTAs used in this project is designed as a two-stage OTA with NMOS input pair and a Miller compensation. All devices are designed to be in strong inversion with an overdrive voltage of 150 mV and a GM over ID of 10. The first stage has a tail current of 10 microamps, while the second stage has a base current of 120 microamps. Combined with an 8 picofarad millicapacitor and a Knolling resistor that is slightly greater than 1 over GM of the output device, a phase margin of greater than 80 degrees is achieved. The gain of this amplifier is greater than 75 dB across all process corners.
Based on the block diagram, we can get the floor plan and corresponding layout. We lay out from left to right according to the direction of signal transmission. There are 68 pins in our chip.
This is the PCB that we designed. In the middle is the chip, and it has a PLC C68 packaging. So let me first talk about the power supply. The power supply for the system is a 4.5 volt AAA battery pack. The 4.5 volt gets converted into two different 2.5 volt rails, one through this LDO, which has low ripple, the other through this buck converter, which has a high current capability. This over here is a potentiometer that acts as the current source, which is the current reference for the chip. Down here are three voltage dividers that provides the voltage references for the chip, including the common mode voltage and two reference voltages for the relaxation oscillator on chip. So for the audio signal, it comes in from this 3.5 millimeter audio jack, and it gets AC coupled and biased to the common mode voltage. Then it goes into the chip, gets amplified, and it comes out connecting to two LC filters, and then finally it connects to the speaker. So because the speaker is inductive, there are going to be overshoot at the output. That's why these four Schottky diodes are added to clamp the output voltage within the forward voltage plus VDD and then VSS minus the forward voltage. After we completed the testing, even though we achieved all design goals, such as a 1.5% third harmonic distortion at 1 kHz 1 volt RMS output, the result still wasn't very exciting, mainly because the power was limited by the 2.5 volt supply. So we decided to add an external H-bridge. A gallium nitride output stage seemed like a perfect choice because it has a very low on resistance while capable of switching very fast due to its low gate capacitance. So we designed a new PCB with two EPC2152 gallium nitride half bridges operating at 12 volts, and we added some new dead time generating circuits and changed the feedback network a bit. As a result, we get a lot more power.